We talk a lot about the cloud, but few people mean it literally. That might be changing. Recently, Jeff Bezos predicted that within a decade or two, we'll see gigawatt-scale data centers in orbit, vast computing platforms circling the Earth, powered directly by sunlight. Sam Altman, head of OpenAI, went a step further and mused about building an entire Dyson sphere of computer nodes around the Sun, a literal solar system-scale AI engine. To many, that sounds like science fiction, but to channel regulars, that sounds like a Matryoshka brain, a type of megastructure devoted to computation that runs on a star in its basement. And we were just talking a few days ago about how you get a Dyson-scale economy to ramp up, so the comment from Altman made me feel like it was a good topic for us today. For many, it sounds like science fiction, and perhaps a full Kardashev 2 megacomputer still is, but there's a deeper point here. Space-based computation might not just be a tech novelty or a distant goal, it could be the next great industry that jumpstarts our long-term expansion beyond Earth. Because if asteroid mining and space-based solar power were the early contenders for a kickstart a self-sustained space economy, orbital data centers may be joining their ranks. So, grab a drink and a snack and let's dive in. The cloud above the clouds. The modern digital world is hungry for energy, for cooling, and for a place to build ever larger computer centers. Every major AI model, every streaming platform, every blockchain, and even this video you're watching runs on machines that burn power. At this point, global data centers consume around 2% of the world's electricity, roughly as much as the entire airline industry, and that demand is expected to double or triple within the decade. In truth, it is the primary bottleneck on AI, and in some ways a bit of a relief. Without some massive revolution in how energy-efficient chips are, or how processor-efficient AI is, we can breathe a bit easier about technological singularities suddenly emerging to wipe us out. And indeed, I'd be much happier to see that develop in space anyway. One of our best hopes for dealing with an out-of-control AI is that it might choose to pack up and leave for greener pastures rather than consuming Earth, and that becomes a lot more plausible if it's already based in space. As we often note, the whole reason we want to mine the moon and asteroids is because it takes far less energy to move resources from them to anywhere in space, even right above Earth, than it does to lift them up from Earth's surface. And with high-efficiency, low-thrust drives, that advantage only grows stronger. But why would we put them in space in the first place? Well, it mostly comes down to power demand. If you want to triple your data centers on Earth, that comes with problems. Data centers need steady power, stable climates, and enormous amounts of cooling water. They are often controversial neighbors, accused of draining local grids and aquifers. But in orbit, you get something no ground-based facility can match: constant sunlight, zero weather, and infinite sky. Space offers uninterrupted solar power, near-perfect vacuum cooling, and no zoning battles with locals. Moreover, it's an interesting example of being obvious in hindsight. Those of us who are space advocates usually assume that we beam power down from space. I still think that's a good option, and the point being we need power down here, but we don't need power down here to run data centers. We need data centers somewhere that have power and come beam results down to us. There is a huge volume of space around Earth within 1 second of light lag to us that gets thousands of times more energy than hits Earth, and most of our big computation takes more than a second. So your ground-based facilities basically handle sorting slow problems. Those that a few seconds or more are fine for, from speed-vital problems and routing those longer questions to big orbital data centers. Bezos has long argued that the future of industry lies off-world. I obviously agree with him, and it's not exactly a surprise since I'm the president of the National Space Society, and he has been a big supporter of the NSS. His view is the Earth should be zoned residential and light industrial, while the heavy work, manufacturing, mining, and now perhaps computing, moves into space. And oddly enough, the math may finally be starting to agree with him. Why move the cloud to space? Well, let's look at the incentives. A data center in orbit could draw limitless solar energy, use large radiators for passive cooling, and run in a near-perfect vacuum where heat dissipation is straightforward. You don't have to pay for real estate or worry about flooding, storms, or overheating servers. There's no downtime, no darkness, and no weather forecasts, just 24/7 sunshine. Down on the ground, even in an equatorial desert, solar is an on and off power supply. Up in space, it is a baseload power supply, one that can reliably produce the same amount of power constantly. There is no non-fossil fuel baseload power generator among our renewables. Only nuclear offers baseload power generation down here on Earth, and while I'm a big fan of nuclear too, a lot of folks are not, and it's created a very harsh regulatory environment that makes nuclear marginally economical. So we need more baseload power generation for Earth, and if we can get that, great. But we can instead shift some of that demand off Earth to a place where it's easy to provide. That's not just a convenience, it's an enormous economic and environmental advantage. Space-based power generation has long been floated as a way to provide clean energy to Earth. What if the first customer for that power wasn't us, but itself, powering the computers floating beside it? A network of solar farms could beam energy directly to orbiting computer platforms, or even just house them right there, sidestepping the difficulty of transmitting power down the grid, or even between orbital stations. That's a profound synergy. Power satellites don't just export energy, but use it productively right where it's made, and it also means that they can create surpluses that we can more economically use on the ground or up in space to kickstart other space industries. How orbital data centers might work. So, how do you build a cloud in orbit? First, you'd start small, perhaps the few prototype modules in low Earth orbit or geostationary, where radiation levels and power access can be tested. One big issue we have in space is cooling. But contrary to popular belief, space is not cold, any more than it's dark. The sun shines there all the time, except when you're in somebody's shadow. We cannot use giant cooling towers. We'd have to radiate the heat away, and probably by having reflective panels bouncing the light away, maybe into solar collectors, while in their shadow, vast radiating fins slowly emit heat as infrared radiation. Each data node could have its own solar array, heat radiators, and communication relays. The data uplink could use laser communication, already tested by companies like SpaceX, Amazon Kuiper, and even NASA, to transmit petabytes of information daily with minimal lag. Yes, latency remains a challenge. Even a low-orbit system introduces milliseconds of delay compared to fiber optics, and that rules out things like real-time gaming or high-frequency trading. Again, you'd still need computers down here, but part of their job would be sorting tasks and kicking those where a little lag is okay up into orbit. And for tasks like AI training, scientific modeling, research, image generation, long-term storage, or even defense systems, that latency doesn't matter much. What matters is uptime, energy, and cooling, and space offers all three in abundance. The architecture could evolve into a cloud constellation, tens or hundreds of modular computer satellites orbiting together, forming a self-repairing decentralized data swarm. Imagine the literal cloud of the future, a glittering network of computation suspended above the Earth, feeding our civilization's insatiable digital appetite. The engineering challenges. Of course, none of this comes easy. Launch costs remain the elephant, or maybe the rocket, in the room. Even with reusable rockets, putting hundreds of tons of processors, solar panels, and radiators into orbit costs billions. Then there's the radiation problem. Electronics degrade quickly in the high-energy particle soup beyond the Van Allen belts. Shielding adds mass, and mass adds expense. Of course, both those problems get easier if you can source most of your shielding material and most of your silicon for glass and panels and chips from the moon, which has a readily accessible abundance of them. And as we mentioned recently in our zero-G manufacturing episode, we've just started producing superior semiconductors in orbit. Vastly superior. So we might start making chips up there anyway, in which case we can then save the cost of having to bring them back down again. Now, maintenance is another concern. Data centers fail constantly, even on Earth, and technicians are always swapping out drives and boards. In space, you either need neat, advanced, automated repair robots or a crude presence, and both require a robust orbital infrastructure that we don't quite have yet. But there's the thing. Those problems are not unique to orbital data centers. They're the same ones facing every large-scale space industry idea: power satellites, asteroid mining, even tourism. And just like those, the early versions will be expensive, inefficient, and mostly symbolic. But symbolic steps often build real futures. Before we go on, I just wanted to mention that we have finally brought back some SFIA merchandise. Folks have asked for it for years, but YouTube finally made a big effort to make this easier for creators to integrate into their channels, and now that I found a high quality vendor, the first batch of mugs is now available over on our Fourth Wall store. They're a great way to support the show and make your morning drink and snack just a bit more futuristic. Use the QR code or the link in the episode description. The economics of a space-based internet backbone. A lot of time when we discuss industry or infrastructure that might help us kickstart space development, what we're contemplating is a loss leader. A loss leader is something you don't make money on directly, but it pays off by opening the door for everything else. Space-based data centers might fit that role perfectly. They would cost a fortune to start, but the infrastructure they would create would make the rest of the space economy possible. What makes orbital data centers exciting isn't just that they are possible, is they could be profitable first. And we're only talking about dumping hundreds of billions of dollars into data center construction, which dwarfs the money involved in NASA or SpaceX or Blue Origins. The business case is cleaner than asteroid mining or lunar helium-3. There is an immediate and enormous demand for computation, and a constant incentive to reduce its earthly footprint. Every watt generated and used in orbit is one that doesn't draw power from the terrestrial grid. Every terabyte processed there frees up cooling on land here, and the infrastructure overlaps perfectly with space-based solar power. If you're going to beam power around in orbit anyway, you might as well sell some of it to a computer farm before you send the rest down. And again, you don't need to beam any power if you hit roadblocks about transmission. Space-based solar has a history of being viewed as basically a death ray. This is wrong, and you can see our episodes on it for why, but it circumvents the issue that the power is all used locally, and the only transmitter on the collector is for the data. Data centers need power, communication, manufacturing, and maintenance, each of which, once built, can support countless other space enterprises. It's not just a business, it's an ecosystem. From kickstart to keystone. Every great frontier began with a single practical motive, profit, transport, or necessity, but ended up transforming civilization. The first telegraph cables weren't built for art or exploration, but they connected continents. The first fiber optics carried phone calls, now they carry the sum total of human knowledge. The first orbital data center could do something similar, become a digital keystone that ties Earth and space into a single continuous network. Just think about how many people a single orbital node might employ indirectly. Launch providers, maintenance engineers, software teams, solar array manufacturers, communication networks, and good jobs too. That's a permanent, paying, and scalable space economy feeding back into the industries that built it. And once that feedback loop starts, it's hard to stop. We could end up with orbital industrial parks, clusters of data centers, solar farms, fabrication depots, and robotic assembly lines all working together. That's how infrastructure grows, organically, one profitable piece at a time. The cloud expands. Every great leap on Earth or in space will start with something small and practical. We build what we need, but in doing so, we build what we dream of. We once thought asteroid mining or power satellites might be the engines that push civilization outward. Maybe they still will be, but perhaps it's the digital ones, the data engines of silicon and code, that blaze the trail first. The cloud above the clouds might one day become the true frontier. Our libraries, our intelligences, our digital civilization orbiting between stars. It won't start with a grand city in the sky. It will start with a server rack in orbit, quietly humming away, powered by sunlight, cooled by the void, and watched over by those who dared to put it there. From there, the rest of civilization will follow.